So today we're going to be talking about Lewis dot diagrams, aka electron dot diagrams. First I'm going to ask you guys a question though. What are the most important characteristics of an atom when it comes to bonding? What did we learn yesterday?
The amount of electrons it has.
The amount of electrons. In particular, what kind of electrons?
Valence.
Oh, good job, Logan. Valence. So, since valence electrons are the important electrons, the most important characteristic when it comes to bonding, we don't really need to worry about those inner electrons. We don't really need to represent those inner electrons. So in the models we use in this class, Bohr diagrams are a great stepping stone. But if you followed along with my lesson yesterday, you will have quickly realized that they're kind of tedious to draw, right? They're super annoying to draw, but they do a great job illustrating that, that full shell of outer electrons when you either lose electrons or gain electrons. So how many valence electrons would an atom of sodium have? 1. Right? So when we're talking about sodium, how many electrons does it have in total? How many does it have in total?
11.
It has 11, right? Atomic number 11, a neutral atom of sodium would have 11 electrons. So those 10 electrons, we really don't need to care about. It's that 1 electron that matters. So an easier model, a model that will help us to do these ionic bonding simulations more quickly is Lewis dots. So what is a Lewis dot diagram? Well, in a Lewis dot diagram, the element symbol is drawn. Surrounded by valence electrons. Because again, those are the only electrons that matter when it comes to bonding. So we don't need to draw all of those inner electrons when it comes to something like a Bohr diagram, right? Bohr diagrams were a useful stepping stone though. So let's explore what that looks like when it comes to sodium. So sodium, the Bohr diagram is kind of a pain in the butt to draw. We have all of these electrons here. And we have this 2 full shells, and then we have that single valence electron. Really, that is the only thing that matters, is that single valence electron. So for a Lewis dot diagram, what this would look like is Na with a single electron, right? It's much, much, much easier to illustrate using Lewis dots. You know what, let's do that same example that we covered yesterday. Chlorine. How many valence electrons does chlorine have? How many valence electrons does chlorine have?
7.
It has 7, right? All of the halogens have 7. So when I draw chlorine, It has a total of how many?
17.
17, right? So, again, drawing that whole Bohr diagram, it's kind of a lot, right? We don't need to draw out all of these inner electrons because they don't matter in terms of the element's reactivity too much. We really only need to focus on these outer electrons. So if I were to draw the Bohr diagram for chlorine, it would look like this. And in the formation of sodium chloride, our ionic compound, what's going to happen? Let's see how many of you were paying attention yesterday or watched the video. How am I going to form this? What does our sodium want to do?
Wants to lose one.
Excellent. It wants to lose one electron because then it will have a full outer shell, right? If we lose that electron, now we have a full outer shell. How about our chlorine? What does it want to do?
Gain one.
It wants to gain one electron. So the sodium here will lose its electron. Chlorine will gain one. And now we're going to be left with two ions, two charged atoms that are going to be electrostatically attracted to one another and form an ionic bond. So our sodium ion, we can represent that as in one of two ways when it comes to Lewis dot diagrams. I'll accept either way. You can either represent it without any electrons around it. This would be acceptable, like this. Or you can represent it with a full shell, because now it does have a full shell. Right? That's the whole reason why atoms form bonds. So you could represent it with a full shell as well. So when it comes to your cations, either way is an accurate representation when we are doing Lewis dot diagrams. With your anions, since they're always gaining electrons, I want you to always show that full shell of outer electrons. So that will be chloride ion. Let's draw that a little further away, make it nice and clear. Chloride ion. Cl minus. So again, you can represent your sodium with a Lewis dot once it becomes an ion. Either way would be correct. Does that make sense? Yes? Okay. So much, much, much quicker and much easier to draw than Bohr diagrams. Again, we lose some information though by going to this more simplistic view, right? We lose those inner electrons. And for some students, they have a hard time envisioning this sodium now having a full shell because we're not drawing that inner electron shell, right? All right. Let's do another example quickly here with the Lewis dot diagram. Let's do the one that took us forever to draw. We're going to use a ratio that's going to give us a lot of atoms in our ionic bond. So let's pick, let's say calcium nitride. So calcium reacting with nitrogen. Now if we look at calcium, how many valence electrons does calcium have?
2.
How many?
2.
Yeah, you're right. So it has 2 valence electrons, right? So how am I going to draw the Lewis dot for that?
2.
2 also makes.
Yeah, exactly, right? It makes it way easier. How many electrons does calcium have in a neutral atom?
20.
It has 20. So I'm eliminating drawing 18 of those electrons. It's way easier to draw. So our calcium as a neutral atom will look like that. Now what about our nitrogen atom? What about our nitrogen atom? How many valence electrons does nitrogen have?
5.
Yeah, it has 5. So our nitrogen atom is going to look like this. So what does our calcium want to do?
Lose 2.
Wants to lose those 2 outer electrons, because then it will have a nice full shell. And what does our nitrogen want to do? To be happy. How will it become stable? What does it want to do?
Gain 3.
Yeah, it wants to gain 3 electrons. Right? So our calcium here is going to lose 2. Right? 1 there. We can draw, that's actually not going to look too well when I do that. Let's do this. Draw 1 there, and let's draw 1 right here. Now is our calcium happy? What do you think? Is our calcium happy? Yeah, right? It's lost those 2 outer electrons, so now it is electronically stable. Is our nitrogen happy? What do you think? No, it's not, right? So how am I going to make this nitrogen stable? How am I going to give it a full outer shell? I'm going to add a, well, yes, I'm going to add an electron. Where is it going to come from? Ooh, let's see, you didn't watch the video yesterday. That's okay. We're going to add another calcium. So our nitrogen's not happy, right? We need another electron, so let's add another calcium to the mix. So this calcium, same thing, it wants to lose those 2 outer electrons. So it's lost 1 now. Is this nitrogen now happy? Is it stable with a full shell? Yes. But our calcium is not, so what do we need to do now?
Add a nitrogen.
Add another nitrogen. Right, we're going to add another nitrogen, and now this calcium is quote unquote stable and happy, right? It has a now full valence shell of electrons, but our nitrogen needs 2 more, so we will add a 3rd calcium. Right, so our 3rd calcium here will donate its 2 electrons away. Whoops, whatever, that's fine. And now every atom has a full outer shell, and all of them are now stable. So, what charge does calcium have now as an ion? What charge does it have? How many protons does calcium have? How many protons does calcium have?
20.
It's 20, right? And in a neutral atom, right, there's 20 protons. In a neutral atom, how many electrons are there?
20.
Yeah, same number of positives and negatives, right? So in a neutral atom, there are also 20 electrons. What did we do? What did we do here? How many electrons did we lose?
6.
No, I'm just talking about a single atom. How many electrons did this calcium lose? It lost 2. So if it loses 2 negatives, how many more positives do we have now than negative? 2. So what do you think the charge is? Positive. What's the magnitude? It's not just positive. How much more positive?
By 2.
By 2, yeah, exactly. So the charge on our calcium ions is now 2 plus for each of our calciums, right? So each of these calcium ions have a charge of 2 plus. I'm going to put that like this here. 2 plus, 2 plus, and 2 plus. Now, what about our nitrogen? What about our nitrogen? negative, what's the magnitude? Yeah, you're right, Logan, what is it?
3.
Yeah, negative 3, right? Because we've gained 3 negatives. I'll do that same thing again. How many protons are there in nitrogen? Always, how many protons are there? 7. How many electrons in a neutral atom? How many? 7, it's always the same. Now we've gained 3, so how many electrons do we have now? If we gained 3, how many electrons do we have now? 10, right? So there's 3 more negatives than there is positives, so each of my nitrogens has a charge of 3 negative. So in total, how many electrons were donated and received? This is an important idea in terms of ionic bonding. It's going to be very important when we start talking about the math, the easiest way to solve these problems. How many electrons were donated and received in total?
6.
Yeah, just count them out. There were 6, right? We have 6 plus 1, 2, 3, 4, 5, 6, and 6 negative 1, 2, 3, 4, 5, 6. So your charges always need to balance. So that was Ca plus, and our other ion was N3 minus, are those 2 ions. Now if I was going to draw them as those dots, again you can draw the calcium like this, or you can draw the calcium like this. Either one would be correct. The nitrogen is going to look like this. So drawing ions is actually really, really easy when it comes to Lewis dots, because what are they always going to have? Think about it. If you draw an ion, what's it always going to have? Why do atoms form bonds? So they can what?
So they can
So they can get a...
get 8.
Yeah, they can get 8. It's not 8 for all atoms, right? There's that exception in the first period, but it's so they can get a full shell of valence electrons. So when you're drawing these Lewis dots for your ions, it's really simple. They're always going to have a full shell. Just be careful of that first period. Okay, any questions at all? Last thing, what will be the chemical formula for our compound we formed here? How many calciums do we have in a ratio to our nitrogens?
2.
We have 2 nitrogens to how many calciums?
3.
3, right? So our compound would be Ca3 and 2. So whenever you looked at a chemical formula in grade 9 between a metal and a non-metal, this was kind of the reason why they formed those ratios. When you're practicing counting atoms, this is the why. So when your atoms form ionic bonds, they will always balance those charges out.